Hello and welcome back to the course. As last time we have seen about the block ciphers and their operation principles of operations. Now today we are going to have the data encryption standard. In this section we are going to see data encryption standard in chapter 2. As far as the data encryption standard is concerned, it is the most widely used data encryption method, and it exhibits the classical crystal structure. As we already discussed about the crystal structure, the data encryption standard has gotten encrypted in a 64-bit block using the 56 key. This is the identity of the data encryption standard. This algorithm transformed a 64-bit input in a series of steps into the 64-bit output. So plain text and the ciphertext length will be same. The same steps in the same key with the same key are used at the decryption side. That means both sides the same key is used. That's why it is called as the most widely used symmetric ciphering method. Now, with the exception of the initial and the final permutation, DES has an exact structure of the crystal cipher. Now, this is the architecture of the DES encryption algorithm. As we have seen, this algorithm is similar to that of the crystal structure. 64-bit plain text is given as an input to the initial permutation. It is producing the 64-bit output, producing the output to the rounds 1 to 16. So there are 16 general rounds are being preferred in the DES algorithm. Then later on, this 32-bit swap is being preferred and to produce a 64-bit output. And the last stage is inverse initial permutation that is produced in order to produce a 64-bit cipher output. That means 64-bit ciphertext and 64-bit plain text. Looking at the right side of the diagram, we will see that 64-bit key is first permuted with the first step of permutation. Then in order to produce a 56-bit key, then left circular shift is being produced, and the second permutation stage is done in order to produce a 48-bit key. So in each round, this process is being carried out in each round, and we are going to have this particular keys for processing in that respective rounds to produce the output of the 16th stage. Now, in this particular case, what we are going to observe is each 56 key is for each round 56 key is used. 56-bit key is used. The key is passed through the permutation function. For each of the 16 rounds, the subkey ki is produced by the combination of the left circular shift and the permutation. Then the permutation function is the same for each round, but a different subkey is produced because of the repeated shifts of the key bits. So this is all about the architecture of the DES encryption algorithm. So overall observations that we can make out from this algorithm is first, the processing of the plain text proceeds in 3 phases. First is initial permutation. Initial permutation is nothing but rearranges the bits to produce the permuted input. Then next stage is a 16 rounds of the permutation and substitution. So these two functions are being carried out into this 16 rounds. The left and the right half of the output of the last round are swapped to produce the pre-output. So pre-output is the last phase in which it is passed through the permutation IP inverse. So inverse permutation, that is initial permutation, is taking place at the pre-output to produce the 64-bit cipher. So this is an example for initial permutation. So 8 by 8 matrix is there, a total 64-bit metadata as a M. Next, the equation for permutation is X is equal to IP of M, and when we take the inverse IP in the inverse permutation, then Y is the output that we are going to get with this equation, right? it can be seen that the original ordering of the bit is restored. It is not going to change. A single round of the crystal cipher, or we can say the DES algorithm, can be shown in this particular diagram. So initial permutation of the plain text is given, which is we can say the division of the left and right bits are being there equally of equal size. With the help of the key K1 for round 1, this function is being executed. This is a as we have discussed about the function for this particular round, the permutation and substitution functions has been carried out, and then it is XOR. Then output is swapped, that is producing the L1 and R1, which is different than the L0 and R0. So this is a first round. Such kind of rounds can be there. N number of rounds can be there in a crystal structures, and every time the key ki will be produced with the for processing of these functions. Details of the single round is there, in which we can say there is 64 bits are like this, 32 bits are, and 32 bits it is divided into left and right again, and the expansion and permutation is being done with the help of the table. The table is given in the page number 75. Then it is again XOR. This key is being used uh, with the XOR operation to produce a 48-bit substitution, and with the S box is produced, which is producing the 32-bit output. Permutation is being carried out, the same 32-bit output is produced, and XOR with the left half of the input plain text, and then we are going to produce this particular output of this particular this one. Now here in this case, Li is equal to Ri minus 1. So this is the output that we are going to get with the help of this right hand side, that when we consider this particular case in which we are going to have this 56 key bit, that is divided into Ci minus 1 and Di minus 1. Here in round key Ki is 48 bits. Now here it is on 48 bits. The R input is 32 bit. This R input is first expanded to 48 bits by using the table that defines the permutation plus an expansion that involves the duplication of the 16 of the R bits. Now the resulting 48 bits are XOR with the Ki, as I told earlier. This 48 bits results passes through the substitution function that produces the 32-bit output, which is permuted as defined in the table 3.2 AD in page number 75. Now this operation can be seen with the help of these equations. Overall processing at each round can be summarized with this equation, that is Li is equal to Ri, as I told, Ri minus 1, and Ri is given as a Li minus 1 into f of Ri minus 1 Ki. The round key Ki is a 48 bit. The R input is 32 bit. This R input is the first expanded to 48 bit by the using the table and defined in the permutation plus an expansion. This involves the duplication of the 16-bit R bit. The resulting 48 bits are XORed with the Ki. This 48-bit result passes through the substitution function that produces the 32-bit output. Now, for the calculation of the f of Rk, we are going to have the 32-bit as an input, and 48 bits are being XOR. This is a kind of adder, and it is going to produce the input to the 8 S boxes, S1 to S8, which is going to produce the cipher outputs with a 32-bit. 64-bit key generation process can be elaborated in this way. 64-bit key is used as an input to the algorithm, and every 8-bit is ignored. Here in this case, the every 8-bit is ignored, because of which we can say this is the key size is 56 bit. The first permutation, so the length of the key becomes a 56 bit. The resulting 56-bit key is then treated as two 28-bit quantities labeled as a C0 and D0. At each round, Ci-1 and Di-1 are separately subjected to the circular left shift and rotation of 1 or 2 bits. These shifted values serve as an input to the next round as well as the permuted choice 2, then which produces the 48-bit output and that serves as an input to the function f of Ri-1 ki. For example, we can take an example of S1. If input is 0 1 1 0 0 1, selected row is 0 2, that is row 2, and the column is 1 1 0 0. Column is 12. The value in row 1, column number 12 is 9. So the output is 1 0 0 1. The counting of the column is from 0 to 15. The DES decryption process is similar, exactly reverse to the encryption. With any fiscal cipher, the decryption uses the same algorithm as encryption, except that the application of the sub keys is reversed. It is written in the page number 81 of the uh, encryption and network system in the William Starling book. Now, cryptanalysis. Cryptanalysis has DES is a strongest weapon against this particular cryptanalysis. We have some come up with certain observations. The need to strengthen the DES against the attacks using the differential encryption played large part in the design of the S boxes and the permutation P. The most of the non-linearity lies in the S boxes, except which the remaining part of the DES is a linear. So there are two major tasks, two major types of the cryptanalysis. First is the differential cryptanalysis, and second is the linear cryptanalysis. So differential cryptanalysis attack, we can say it's the rationale behind this differential cryptanalysis is to observe the behavior of the pairs of the text blocks. So this is all about the differential means it is about the pair of the text blocks evolving from evolving along each round of the cipher instead of the observing the evolution of the single text block. Now consider the original plain text block M to consist of two halves M0 and M1. So each round of the DES maps the right hand input into the left hand output and sets the right hand outputs to be the function of the left hand input and the subkey for this round. So differential cryptanalysis can be elaborated with the mathematical equations. Each round only one new 32-bit block is created, mi plus 1. It is written with the mi minus 1 XOR of f of mi ki, where I is a number of rounds, that is 16 in this case. The differential cryptanalysis is that we start with the two messages m and m dash with a known XOR differences dm is equal to m XOR of m dash. Therefore, the resulting equations we have delta mi plus 1 is equal to mi plus 1 XOR of m dash of I plus 1. So it can be written as mi minus 1 XOR of f of mi ki XOR of mi dash I minus 1 XOR of f of mi dash ki. Resultantly, we can say del of m of I minus 1 XOR of m f of I ki XOR of f of mi dash ki. So the observations from the differential cryptanalysis is if we know dmi minus 1 and the dmi with high probability, then we know the dmi plus 1 with the high probability. Furthermore, if a number of the such differences are determined, it is feasible to determine the subkey used in the function f. Linear cryptanalysis is second type. In this attack, based on finding linear approximations to describe the transformation performed in DES. This method can find the DES key given 2 raised to 43 known plain text and compared to the 2 raised to 47 chosen plain text for the differential cryptanalysis. So it's very clear about this cryptanalysis methods. Now we are going to have the block cipher design principles, and then following are the basic design principles. First is a DES design criteria, which is focused on the design of the S boxes and the P functions. Next is the number of rounds. The greater the number of rounds, the more difficult it is to perform the cryptanalysis even for the relatively weak functions. Next is the design of functions. F relies on the use of the S boxes. Next is a design criteria for F. F provides the element of the confusion in the Fister cipher. As we have already discussed about the confusion, Fister cipher, so F should be non-linear. Next is a S box design. Any change to the input vector to an S box should result in random looking changes to the output. The relationship should be non-linear and different and difficult to approximate with the linear functions. Next, and then the last one is key schedule algorithm. Subkeys should be selected to maximize the difficulty of the deducing the individual subkeys. So, some observation that we have made is necessary to have the replacement of the DES was needed as the theoretical attacks that can break it. Then a differential has a chosen plain text and the linear has a known plain text at 2 raised to 47. And the brute force, if it is being attacked, then it is easy for the cryptanalyst to decrypt the DES algorithm. So the further developments for the cipher year wise or the text size and key size wise is first this algorithm, which is a crystal structure invented in 1973 using the 64-bit text size and 128-bit key size. DES invented in 1977, 64-bit text size and 56 key size. So it is a SDES. It is called double DES algorithm, which is invented in 1996. 8-bit key size and 10-bit text size is 8-bit and 10-bit key size. Triple TES and AES are the advanced encryption standards which are being preferred for the replacement of the DES, which are invented in 1999 and 2001 respectively. These triple TES uses 64-bit text size and key size is 168 by 2 3 keys. Now we are going to see the details about the 3DES also. Advanced Encryption Standard invented in 2001 uses a text key 128-bit and key size 128, 192 or 256-bit. 3DES, Blowfish, RC5 and RC4. These are the invention years, and the key size is text size is 64, 32, 64, 128 for RC5, and for RC4 it is a byte stream. Key size which are for Bluefish is 32 2448 variable, and RC5 has got a 0 to 2040 bits variable. Now RC4 it is a 1 to 256 bytes. Then if you compare in terms of making this particular rounds as well as clock cycle per round or number of the clock cycles per byte encrypted, here in this case for Bluefish, RC5, DES, the 16 rounds are preferred, but for idea algorithm only 8 rounds are required, and for the triple DES 48 rounds are required. So more complex DES is triple DES. The solution is to provide the new algorithms, that is advanced encryption standards, and use the multiple encryption for the current sequence is 3DES. That is example of or next type level of algorithm is 3DES. Thanks for watching.